Well, greetings, Mr. Colazar's class. Today we're going to be looking into this idea of radiation, the idea of radioactivity. So what we're going to be looking at is an unusual form where we have an unstable nuclei and how it's going to actually decay. So we're going to be looking at things that are called our alpha, beta, and gamma radiation in terms of symbols, mass charge, shielding materials, and energy. So to describe this, first off, we're going to go back a second. Difference between chemical and nuclear reactions. The following example is a chemical reaction or a chemical change, things that we've been looking at up until this point. Note that the starting substances have changed, but the elements involved have not. So this would actually be combustion. This is methane, which would burn in the presence of oxygen to give us carbon dioxide and water. So during this reaction, we'd actually producing fire during this reaction, but note the carbon and the carbon are still the same. 4 hydrogens over here, 2 times 2, 4 hydrogens over here, 2 times 2, 4 oxygens over here, and 2 plus 1 times 2 is 4 oxygens. So we have the same amount of each elements on both sides. The substances have changed, but the elements remain the same. So that's our idea of a chemical change. So now what we're going to look into is around the 1890s, scientists started to notice substances emitted radiation, and they called this substance or this idea radioactivity, where energy was being released. The rays of these particles emitted were called radiation. So radiation is that radioactivity, the energy being released. So we're starting to call these now nuclear reactions, where there's a change to the center of the atom where the nucleus is, and so thus changing the elements. So we're changing those protons and neutrons in that nucleus. Therefore, we get different elements afterwards. So this would be an example now of a nuclear reaction, starting with thorium-235 over 90, so element 90 on the periodic table. It's going to go through a nuclear change where we have a different element afterwards. In this case, what do we have? Praseodymium-235 over 91 plus some sort of information or some sort of energy is being released here. So this is some sort of energy or radiation. We can just put that example just on your note packet there. So note the starting element has changed into a new one. So we have a different element afterwards. From beginning to end. So this would be an example of what's called a nuclear reaction. Different element being produced. We're changing that nucleus. So when we start looking at this, recall, remember, isotopes, atoms belonging to the same element, same number of protons, but have a different number of neutrons is what an isotope is. For any given element, that ratio of protons to neutrons determines its stability. So how stable, how likely is that element just to stay as it is for the atom? If the ratio is unstable, then the atom will undergo radioactive decay. These changes can occur once or many times until a stable ratio is made. So a lot of times an element is going to go through from one to another to another to another as it continues to break down until it finds some stable point. So like example here, carbon 12 versus carbon 14. Carbon 12 is our stable version. Carbon 14 unstable and decays over time to different elements to making it to a stable one. So from there, this is going to be our key table. So kind of just pause for a moment and get this table copied in. So let's pause. We'll get that table copied in so that we can start discussing it. All right. So now that you've finished up that table, alpha particles is going to be our first type of radiation. So alpha particles are going to be using the symbol either the helium or the alpha symbol, which looks like a little squiggly. There we go. And then 4 over 2. So basically it's very similar to the helium atom when it has its mass. Mass of 4 atomic mass units. Its charge is a +2 overall. So basically it's the helium atom without the electrons. Shielding, what stops it? Energy-wise, paper or skin can block it, so it's not a very strong, very low in energy. Our second one is our beta. Beta, kind of that little bit of a squiggle B or cursive B there, is going to be known as a 0 with a -1, or that electron, or with the beta. So you can say either term for the beta particle. It's kind of like an electron, basically. It's got a charge of -1. It's a very small amount of mass, so it's very similar to an electron, is what the beta particle is. Aluminum foil would be thick enough to stop, so it's kind of got a medium energy to it. And our last one, no mass to it. Gamma has that kind of almost like a Y symbol to it. Gamma has no mass, no charge to it, but is a high energy amount being released. So thick sheets of lead, meters of concrete is what's needed to stop this from penetrating or going through a material. So our three that we need to use, the alpha, beta, and gamma particles, are what's going to be released during energy. These two, the alpha, beta, are going to the primary ones to know about. Will always give you if there's going to be gamma radiation included. So when we look at that, alpha, beta, gamma particles, alpha is basically 4, 2 protons, 2 neutrons being released, would be blocked by a piece of paper, very low energy. Beta is kind of like an electron. It's able to get through paper, would be blocked by aluminum foil. Gamma is just high energy, no mass to it, able to penetrate both paper, aluminum, and actually go through lead and concrete, with a little bit being stopped, but some actually getting through. Gamma is the one that's dangerous to us, so we've got to be careful about the gamma radiation. So that's the one that you're most worried about. That one's the one that can damage cells and cause problems there. You might be able to get superpowers from it if it is the movies, but overall probably not going to happen in real life. So noticing that, just going through that chart, that alpha, beta, and gamma particles. Now where we can see these, just so you have them for the future, gold packet, page 4 for their references. And the ones to focus in are these first two, and then also that third one. But the alpha and beta particles are the ones that we're going to be most concerned with seeing, looking at what they're actually producing. So as we're working, those are going to be the two from page 4 of your gold packet that you're going to really be needing to see. Gamma radiation will always give to you if it's included. So what does this actually look like? When we do this, rules to write at the bottom of your page. They're not on there. We need you to write these at the bottom of the page of your notes. So rule 1, right, top, bottom numbers must add up and equal each other on both sides of the equation. So the top numbers must equal, the bottom numbers must equal. Second rule, bottom numbers, the atomic number determines the element or radiation type. So when we look here, our first rule says top and bottom numbers must add up to be equal. If we notice, we've got 234 top number, 234 top number here. So 234 and 234 are equal to each other. So in the end, 0 would be on top. 90, to get to 91, we need -1. So when we look at that, we are going to call that 0 of -1 is our beta decay. So we're going to use that symbol B, or you can use the E- symbol. Either one will work. We're going to call that the beta decay. So to go from these two elements, what we're looking for is that beta decay to occur. So looking at another example, we start out 220 over 86, but we've got something plus, so what plus 220, or what plus 4 equals 220? So we would need, well, we're not going to do that one. We'd need something around 216. And then at the bottom, 86 to 80, what, plus 2 to get to 86? We need 84. So in the end, 216 over 84 polonium is going to be what we have, plus the 4 over 2 particle, the helium, is going to be that alpha particle decay. We call it alpha. So we went from 220, 4 plus 216 gets us to that 220, 2 plus 84 gets us 86, and then polonium, element 84 from the periodic table, we'd figure out that that element was polonium. Now for this last example, we're starting out with magnesium, and magnesium is turning into aluminum, and it's also already just given to us that we have gamma radiation. So to go from magnesium to aluminum, we went from element 12 to element 13. So what plus 13 gets us to 12? It's that negative 1. So when we're looking at negative 1, 23 to 23 is 0. So we have that negative 1 is our beta decay that's happening. What's going on is we have a neutron turning into a proton for this reaction to occur. So in the end, what we're looking for is that difference between the start of the reaction and our end of the reaction must have those same numbers included between the two. So when we go back, first off, top numbers must add up to equal each other on both sides of the equation, and then the bottom numbers must equal each other both sides. That bottom number atomic number determines the type of element and that radiation type. So we're going to let you go ahead and get started. You can begin working on finishing up our worksheet packet now. Besides that, safe travels to everyone.